So good morning students. Today we will be having an introduction to the Transducers Engineering Unit 1 which covers the units and measurements with standards. So let's directly go to the unit. We are going to have the beautiful subject of Transducers Engineering, which forms the basic building blocks of instrumentation. As we all know, we have the six senses: the touch, sense, vision, and all these things are the six senses that we have in our natural everyday life, and these needs to be transformed into some artificial things using the senses. There comes the play of senses in the humankind. Here we are transforming all this vision, touch, and all the six senses into machine readable format using these elements known as senses. There are different varieties of senses that which we can categorize them, and we will go for that later. First we will start with the basic physics called as the units and measurement. Units and measurement. Units and measurement, as we all know, which we have studied from the very elementary school level, it has the fundamental units and the derived units. This is for the units. And for measurement, we have a standard system called as the SI unit system, which comes from the word system internationally, that is the French word for international system of units, as because till today we have all our measurement standards being placed in an office known as International Bureau of Standards in Paris, from where this SI units comes from. Now let's come back to our fundamental units. These fundamental units are totally irrelevant units. Fundamental units are not related to each other. There are 7 fundamental units altogether. The basic thing is to measure length, which is represented by a unit known as meter. The next one is mass, which is represented by kilogram or kg. Third one is time, which is represented with the unit of seconds. The fourth one is amount of substance, that is mole. Fifth one is luminous intensity, which is candela. Okay, and the fifth, sixth and seventh one will be introduced to you in the later stages of the higher studies. Now, using these fundamental units, we are going to derive the all other units in our physical world or in our chemical engineering. How we are going to derive all these things? For example, we will take area of a square. What is an area of a square? It is represented with meter square. This meter comes from length and it's also squared. So area's unit is meter square. Then volume, okay, then it comes with meter cube. So volume is meter cube. Both this area and volume are derived units. Okay, I tell you a very basic example of area and volume, and both these things are derived units. Maybe we can take some a little bit to the next level of derived units, that is frequency. As everyone know, what is frequency? is cycles per second. Cycles per second, that is represented as 1 by s, that is like this. So this is the derived unit. Okay, so frequency is, we are representing with the unit of s to the power of -1, and it is the inverse of seconds, and hence it is as a derived unit we are representing it. Then comes force. What is force? It is, we have the unit named as Newton, that is kilogram meter second square. Okay, it is the amount of force that is put up over a length in second squared. Okay, that is what we see in Newton. Okay, and this also applies for pressure. Here it becomes Pascal in the normal terms, represented with the unit of Pascal, and here it all becomes reversed. Okay, so these are all derived units. Okay, here what we saw, the area, volume, frequency, force and pressure, which are normally represented as meter square, meter cube, and cycles per second as s to the power of -1 and Newton and Pascal. But here we can represent this Newton and Pascal as the normal fundamental units like kilogram multiplied by mass into second square, and here the inverse. So now we have got an understanding about the fundamental units and the derived units. So this is the basic building block of any kind of a measurement and instrumentation subject. Without the knowledge of any kind of these units and standards, we will not be able to move forward for any more understanding. Now we have very well understood the concepts of units and measurements with the standards. That is, the standard is the SI units we are taking in. The SI units are being followed all over the world except few countries to the day-to-day life, like USA is not following it. It has its own British system, already established British system, the pounds and yards, etc. But that's also only in their everyday life they use it. But when it comes to the technical world, they use the SI units. And also Myanmar also is not using their own units, they are using it. But when it comes for the technical world, the entire technical world is just rely upon the SI unit standards only. Now let's come back to our subject of units and measurement. We have now have a good understanding of fundamental units and derived units. Now the next one starts with how we are going to utilize this units and measurement for our transducer engineering. For this understanding, we need the basic understanding of error analysis. Error analysis. Why suddenly we are jumping from units and measurement, which is a basic understanding of physics, to the error analysis term, is because any measurement, okay, is simply a comparison with the standard. Okay, any measurement. Some funny things over here. Previously, yard was used in British console. Wherever the British Empire went, they used the unit named as yard. Okay, what is yard? It is simply the distance between the nose and the distance of the hand tip of King Henry III. Okay, so they just totally removed this concept of yard, and now we are having meter. And in what is meter? They have a distance put up over there in the Paris in a platinum iridium rod. Okay, previously, and now they have a laser instrumentation for meter, and two scratches are made over the rod, and the distance between the two scratches give you the meter, and from that every meter is taken. Okay, this is the basic of taking a unit or a standard. Okay, the standard now lies there in a Calibration Bureau. The International Calibration Bureau is set up there in Paris, and our National Bureau is set up there in Delhi. Okay. So this is what we do there in the error analysis. Now, the error analysis is taking a true value from the measurement and comparing it with the measured value. Now you need to understand what is true value and measured value. Okay, and this process of comparison between the true value and measured value is called as static calibration. Now you are very well now getting introduced to the most important term of instrumentation, that is calibration. Okay, calibration is comparing the measured value with a standard value, and here I am taking that standard value as a true value. Okay, now I will define what is true value, then only you will be able to understand what we are going to do with this calibration. Okay, I am going to define true value. True value. Okay, true value is you are going to take the measurement repeated infinite number of times. Infinite number of times a measurement is taken. Okay, and the average deviation, the mean deviation should be 0. Okay, we are going to take a measurement infinite number of times and the mean value or the deviation from its mean should be 0. Is it possible in reality? For sure not. It's not possible in reality. Okay, hence this obtaining a true value is not possible in reality, so it's an impossible thing to get a true value. So we need a standard. Okay, we are taking a standard for this. What is a standard? A measurement standard is a reliable source of information taken from an instrument that is calibrated against a standard instrument. Okay, now you have your thermometer or else a 1 meter scale there in your physics laboratory, and you believe that the scale or thermometer gives the correct reading. Why do you believe that? Because that is calibrated against a standard instrument. Okay, that is the reason that you believe that that is giving the correct value, and you go in for taking the 1 meter scale and measuring it with for the 1 meter, or else you take the thermometer and you take the thermometer readings, and if you have invented a new thermometer, you can take the thermometer and compare it with the thermometer that is available in the laboratory with your new thermometer that you have invented. All these things are possible, only possible, and if only possible if that thermometer available in your physics laboratory is calibrated against a standard. So when they obtain from their vendor itself, they will check for the calibration certifications whether the vendor has calibrated all the thermometers what they buy or the instruments what they buy against the standard, and they are so that the instrument is reliable and it gives the perfect answer or it gives the error very limited. Okay, now you see I have uttered the value error over here. Okay, now you need an understanding of error to understand what is the meaning of calibration. Okay, now we come back to what is the meaning of standard. As I told you, this is the available calibrated instrument to compare. Okay, so it's available calibrated instrument to compare your own instrument so that you can obtain an error. So now this true value is being replaced by this standard value, which is obtained from the standard instrument. Then comes your measured value. That is so simple. That's what you measure there in your laboratory from normal means that you measure from your own instrument, or what you have invented, what you have been measured is it's in the measured value from the parameter being measured. Okay, so it's very clear that we are having two types of parameters. One is the standard value and then the measured value. The standard value comes from the calibrated instrument so that it can be taken as a standard, and a measured value comes from the measurement experiment which you are going to make. So these two are the values. Now comes the concept of error. Error is the most important factor which you are going to have everywhere in instrumentation and transducer engineering. Wherever you go in instrumentation, you are going to have the concept of error. Okay. So how are you going to calculate error? Let's take error as a delta E. Okay. You are going to take this value of standard value as delta S, okay, measured value as delta M, okay, and delta M minus the delta S gives you the error value of delta E. Okay, you are going to subtract the measured value minus the true or standard value. Okay, that will give you the error. So now you got the concept of error. So error is the deviation that is we have occurred from the measurand. Measurand is the measured value. Okay. So we need to correct this error. How are you going to correct this error? By taking a correction value. Okay. Now correction. Correction is simply the reverse, that is the delta S minus the delta M, which is the standard value minus the measured value. Okay, finally you will get the correction. Okay, I will now give you a small problem on finding out the error and giving its correction. Let's take the standard value that you perfectly obtain from a thermometer for the boiling point of water. What is the boiling point of water? Everyone know it is 100 degree centigrade. Okay, centigrade is the unit. This is a fundamental unit, temperature. Okay, so standard value of boiling point of water is 100 degree centigrade. Now you have designed a thermometer using some several other elements, and then you want to check whether is it correct, what is the error value that you are getting. Okay, all these things you need to check. Okay, so now the measured value, you are taking a water bath and instead inserting your standard instrument, and you are inserting your instrument. This is the measured output, and you are getting something like this. Okay, so you need to calculate now the error value and also the correction factor for all these things. Error is what? 100 degree minus 102.4 degree centigrade. So the value is equal to minus 2.4 degree Celsius. Okay. So it is deviating around 2.4 degree centigrade from the true value or the measured value, standard value. Okay. This standard value now have an error of minus 2.4 degree centigrade. if we need to correct this minus 2.4, what we need to do for our measured value, we need to add up. Okay, we have to reduce 2.4 degrees is the error. Okay, see the correction. 102.4 degrees centigrade minus 100 degrees centigrade is equal to 2.4. Okay, so this is the correction. If you make this correction for all the measured values, okay, plus, okay, if you make this correction possible, okay, then you will be able to get, okay, this standard value. You need to subtract 2.4 degrees centigrade from the values that you obtained from the measured value, so that you will be reaching to the standard value and you will be able to calibrate the setup. For this reason we got these two concepts of error and correction here. We will now move on to the most important things of transducer engineering. The next comes, we have completed the most important static calibration, and now we go for static characteristics. For any system, now we will just have an introduction to our sensors on a systematic basis. In any process or a system, okay, has its own static characteristics and dynamic characteristics. Okay, the characteristics are divided into static characteristics and dynamic characteristics. What are static characteristics and dynamic characteristics? The static characteristics don't change with time. Okay, and the dynamic characteristics changes with time. They are time invariant. Okay, this dynamic characteristics are time variant. Okay, and we are going to see today in the part 1 only the static characteristics of a sensor. The sensor is considered as a system and we take all the static characteristics for our sensor. I will introduce you to the terms of static characteristics. What are all the characteristics that we are concerned with and what we will be seeing it here. The first one is accuracy. The second one is the most important, precision. The third one is range. The fourth one is span. Fifth one is sensitivity. Sixth one is reproducibility. Seventh one is drift. Okay, these are the most important characteristics. If anything adds up, I will be giving you in the next lectures. Okay, today we will have an outlook over the most important first 4 characteristics. We will start with accuracy. Accuracy and precision, these two are very important as these are misinterpreted in most of the cases. Okay, most of the people can't differentiate accuracy and precision. Okay, but I will clearly explain you with some few diagrams so that you can understand the concepts of accuracy and precision. Now see here, what is our aim? If a person gives a bullet shot, he likes to give it exactly over here. Let's take, we are going to give him a chance of n is equal to 10 times. He is going to give a chance. Okay, and one for the first person, this is the first person, second person, third person, and then the fourth person. Okay, the first person hits like this. He hits exactly at the center, perfectly matching the center point. Okay, he is hitting it. The next person hits it something like this. The third person hits it something like this. Okay, the fourth person hits it like this. So have you interpreted what is happening in all these four cases? I give you some time and then you please interpret what is happening in these four cases. Okay, and these four cases define both accuracy and precision in a very precise manner, and you'll be able to understand accuracy and precision from these four diagrams. Let me start explaining you. The first person is high accuracy and high precision. Second person is very low, that is low accuracy and very high precision. Third person is medium accuracy and medium precision. Fourth person is very low accuracy and low precision. Are you able to guess what is really happening here? The first person is very high accuracy and very high precision. The second person is very low accuracy and very high precision, because our center point is over here. He is able to shot at a distance somewhere, but at a very high precision. He is only targeting this region. For 10 shots he have made exactly at the one point. Okay. The third person, he is able to shot at around the single circle, so only we are having medium accuracy and a medium precision, and then finally the next fellow can't shot at anywhere, hence it is a low accuracy and low precision. This now apply this concept of 4 persons shooting the 10 bullets to your instrument. Now let's consider this concepts to 4 different kinds of instruments. Okay, the persons can be replaced with the instruments, and the same thing will be applying over here for accuracy and precision. Okay, so the first instrument, okay, this center point, the center point is your standard value. Okay, the center point is your standard value. So only I mark it exactly in different color. Okay, your center point is your standard value, and this person have shot it with very high accuracy and normal precision. Okay, so only I put up a high precision. Okay, the first instrument, okay, the first instrument has a standard value being located somewhere. Okay, let us consider it is as 100 degrees centigrade, and then you are measuring it with a new instrument. Okay, and it is giving some 10 values. Okay, now I am writing those 10 values like this. You see here, this is your standard value versus the measured value for boiling point of. The standard value will be always 100 because it's a very precise instrument. Okay, the measured value for the first one will be something like 100.2, 99.4, 100.5, 101.1, 99.0, 98.9, like this it goes on, just circulating around the center point. Okay, with high accuracy and high precision. Okay, this is the first one with high accuracy, and high precision. Okay, the next one is with low accuracy. So let us consider something like 30 we are getting, but with very high precision. So it is 30.0, 30.0, 30.0, just to 30.1, 30.0, 30.1, 30.1, 29.9, something like this. Okay, so it is with high precision, low accuracy. Okay, the third one will be in a distributed fashion. Okay, something like 95. It is with medium accuracy and medium precision. So it is something like 98.9, 96.5, 94.8, 103.2, 102.1, something. It goes on oscillating between these two in this around this range. The last one will be some observed values, low accuracy and low precision. 30, 29, 40, 103, 102, 30, 20. Like this it goes on. Okay. So we have now very well understood the concepts of accuracy and precision now. So what is accuracy? Is the nearness to the ideal value. Okay. Our ideal value here, the standard value is the boiling point of water, and how much our measured value is nearby gives you the accuracy. What is precision? The reproducibility of that 10 times. They are taking how many times you take, how much good it reproduce itself. Okay, that is the precision. Okay, first instrument, second instrument, third instrument, and the fourth instrument. Okay, we have marked all those things here. Okay, finally we come for our range and then the span. Okay, range and span are very simple some terms here. Your instrument can measure, that means you take a laboratory thermometer. Okay, again imagine a laboratory based thermometer. Okay, that can measure -10 to +110 degree centigrade. Okay, this is your range from the minimum value to the maximum value, that is -10 degree centigrade to the 110 degree centigrade is the range. Okay, and the span is your maximum value minus the minimum value. So it is 110 plus 110 is your, plus it won't come, something a modulus is your span. Span is 110. Range is minimum to the maximum, and the span is the distance that it can measure. The maximum minus the minimum is your span. Okay. So now we have come to a good understanding about the static characteristics. The first four features, that is the accuracy, precision, range, and span. Okay. So this concludes the part 1 of our lesson. Thank you.